let's look at some of the basic discrete sequences examples. First one is the discrete delta function, which I am shown here. All discrete sequences are sum of the addition or sum of time shifted and scaled versions of discrete delta functions. Then the next one is a typical finite length discrete signal. We can see here it has it's a length 50 finite length sequence. This is what we will be encountering generally in real life situations. And then we have a typical periodic sequence, like it's some sinusoidal at some frequency. So these are some of the examples of a typical discrete signal. Okay, so that was some description about the discrete signals and how should they be treated. Now let's look at discrete systems. So what are discrete systems? If we have to answer this question, they can be understood as algorithms or blocks which will take discrete signals as inputs and then manipulates them, performs some calculation on them, and output another discrete sequences as output. Now one can design any system, but that will not necessarily be realizable. By realizable, I mean we will not be able to implement it in real hardware or software. Only the systems which consume limited computational power or MAC operations. MAC stands for multiplication and addition computation operations and takes up limited memory can be realized. Realization can happen either on hardware or in software. As we will see on the next slide, I've shown how the same digital system can be implemented both on hardware or on software, depending upon different requirements. So I'm showing a typical FIR implementation here, FIR finite impulse response implementation here. Left-hand side shows a hardware implementation where we are using blocks, the delay blocks and adders to implement the FIR operation. This is a 8-tap filter implemented here in hardware. The same filter implementation can be done in software also, where we have some C code running on the chip or some assembly language code running on the chip, which will do the same FIR operation on the inputs. So in general, this is true for any realizable DSP system. I mean, it can be implemented in hardware or in software. And the decision depends on computational complexity or real-time constraints, like how fast the results are required and so on. Then there are certain properties of discrete systems which one has to understand in order to design them. Like I have shown here, we have stable systems, we have linear systems, time invariant system, and causal systems. Now, the problem which we are trying to solve can require the system to be linear or causal. Most of the practical systems are LTI systems called linear time invariant systems, or are required to be LTI systems. Most of the practical systems are required to be LTI systems. Why, we will see later. Many real life systems over which we do not have control, like the multipath wireless channel that I shown earlier in the slide, the slow and fast fading channels are sometimes modeled as LTI systems so that we can simplify their analysis and we can study and develop algorithms on them. LTI systems are so important because they are completely characterized by their impulse responses, like I've shown in this figure. If this is an LTI system and this is the impulse response of that system, we will completely know, I mean, everything which is there to know about that system. We will know its the input-output relation, the frequency response, how it will modify the frequency related information which is there in Xn and output Yn. So any arbitrary input, any input you can provide to the system, we will know what is the output. This is a huge advantage since the input-output relation is given by convolution operation, which I have shown here. This is the convolution operation through which we can know the output of an LTI system. This is true only for LTI system. This relation holds only for LTI system, and that is why the implementation of an LTI system, or the requirement that the system has to be LTI, is so important. Yeah. So once we have, I mean, this is a huge advantage because convolution of discrete sequences involves just multiplication and addition. As we can see here, we are just adding and multiplying, and these operations are very cheap in DSP processors. Okay, this brings us to the Fourier analysis of discrete sequences. Once we have understood the signals with the discrete signals as vectors in vector spaces, then we have to understand the DFT or Fourier analysis as linear transformation of these n-length vectors. What we are doing with these vectors when we are taking DFT is we are changing the basis of these vectors from the time domain canonical basis to Fourier discrete basis. And this change of basis comes from the linear algebra concepts, and the tools from the linear algebra are used here. And once we start using linear algebra, we have all the tools from linear algebra available to us to be applied in DSP. And then we can extend this idea of DFT or change of basis to periodic signals. And Fourier transform of periodic discrete signals are called DFS, which is the discrete Fourier series. And then we can extend the idea to infinite length sequences, and then so Fourier analysis of infinite length sequences are called DTFTs. I'll show the expressions in the next slide, which is the discrete time Fourier transform. So this slide shows what it means when we say that, or when we take the DFT or discrete Fourier transform of a discrete sequence. So we have input sequence here, which is xn, which I have represented as a vector. This is a finite length sequence, and what we are doing is we are projecting this vector on different Fourier bases. So these are the different Fourier bases, which are representing different frequencies. And when we project this discrete signal on different Fourier bases, we are actually finding out the similarity of this input signal with these with these distinct discrete Fourier bases. And this similarity is then become, I mean, this is represented as the DFT of the input. So this transformation takes the time domain discrete signal to frequency domain discrete signal, and particularly this discrete sequence. So we can see that the information revealed by taking this DFT is of a different kind. So here we have time domain information. We can see how that signal is varying in time here. And once we take DFT, then we can a frequency domain information is revealed about the signal. So here we can see what kind of frequencies are present in the signal. So from the picture, we can see there are low frequency components more than the high frequency components. So this is particularly a low pass signal because we have very high energies of low frequency components in this signal. So I have shown the expression of this DFT and DTFT of any discrete sequence. And from the expression, we can see that these sequences are actually 2 pi periodic. So if we replace k by k plus 2 pi, the expression will not change, or the result will not change. Here also omega represents the digital frequency, and if we change omega by omega plus 2 pi, the expression remains same. So in discrete domain, we have frequency only from 0 to 2 pi or minus pi to pi, because after that the frequencies start to repeat themselves. Okay, so we have certain properties of Fourier transforms of discrete sequences. which are like very much similar to the Fourier transform of continuous time signal, but there are some differences also. What I have shown in the first row here is this is a real valued discrete sequence, and I've taken the DFT and shown the real and complex components of the DFT of this signal. We can see that when the signal is a real valued signal, the real part of the DFT is symmetric around 0, and the imaginary part of the DFT is anti-symmetric. And the phase is shown here in this plot. Now, if we revert this, if we take DFT of the time reversed version of the signal, so I've just taken the same signal and reversed in time, we can see that the real part remains same, but the imaginary part is inverted now, and so is the phase. It was having a positive slope here, now it is having a negative slope. The other very important property of DFT is time shift property. So if I'm not sure if it is visible, but I have pulled the signal a little bit back by giving it a time shift of some samples, let's say n0 samples. And how this manifests is we have the phase ramp multiplied with the original DFT. So that is visible from the phase plot. So we had straight lines here and some slope. That slope has increased, and the straight line, we can see that phase ramp in the straight line portion. So this, we can see that the straight line has become achieved some positive slope here and here. So these kind of properties and insights into these properties are important to understand the nature and behavior of discrete signals and systems. Now, after that, I don't have a slide on Z transform owing to the time limitation. What I'll do briefly, I'll talk about this important technique. Z transform does not offer any new insight into the nature of sequences or systems, but it provides us with a tool to map complex valued sequences into complex plane. It is used in solving what we call as CCDEs, which are constant coefficient difference equations. So these are discrete domain equivalent of differential equations. So in continuous time, we have differential equations, and in discrete domain, we have difference equations. And Z transform further provides with mathematical ease with which we can characterize stability of designed filters or any DSP block, particularly if the region of convergence of the transfer function of a system contains a unit circle, then we say that the system is stable. Generally, we are designing a discrete system or algorithm when we are designing any algorithm for performing some operations on the discrete sequence, then we have input-output relation in form of CCDEs. Now, if we take the route of finding out impulse response of the system first and then analyze its frequency response behavior, it can sometimes become very complicated. So Z transform comes to our rescue in these situations, and using this Z transform, we can directly map the CCD to transfer function and then understand the frequency response without the need to compute impulse response of the system. So these kind of analysis is very easy through Z transform. That is why it finds a crucial place in fundamental concepts when we are talking about DSP. Then we have the last of the fundamental topic, which is sampling and interpolation. So this is the technique through which we take the continuous time signals and bring it into the digital domain. We sample the signal with some sampling frequency or add some sampling duration. Now, there are baseband sampling and bandpass sampling techniques. Baseband sampling technique is when you have a whatever signal you have. I have shown in this diagram here. This is the original signal, the blue ones, and this is a real valued signal. That is why we are having the negative frequency spectrum and the positive frequency spectrum, and they are symmetric about 0 hertz. So baseband sampling is based on the Nyquist criteria of sampling, where we choose the sampling frequency to be double the maximum frequency component. So here, if this is the maximum frequency component, then we will choose double this frequency, double of this frequency as the sampling frequency. This will not be desirable in many applications. Like I have shown here, the maximum frequency component can be too high, and to have a system which is operating at that high sampling frequency is very expensive. The clock running, I mean, the clock which is running that system can be very expensive. So what we do is band pass sampling, because uh, even though the maximum frequency component is here, but the signal is limited to this band of frequency only. So we can utilize the band pass sampling in this scenario, and we can instead of sampling at 4 fs, we can sample at only half of this frequency. I mean fs, and that will create images of these spectrum at this and this frequency and here, and then we can use a low pass filter to take out this spectrum, and then we will get our signal back. So band pass sampling is utilized when we have a band pass signal, and it is a very important technique in all of the applications that I have talked about. Then we have interpolation techniques, which is the reverse of sampling. We have to take the signal from digital domain to analog domain, because any real physical output, like if you are listening to a music, that music is a continuous time signal which is coming out of the speaker. Whatever digital domain processing you are doing or happening in digital sequences, that is okay, but the final output has to come into the real life as a continuous time, so that you can you can use that signal. So interpolation is the technique where we fill the gap between discrete samples of the signal. So we have different techniques like local interpolation techniques and polynomial interpolation, where we uh, uh, sample or interpolate the signal using cubic or fourth order or fifth order polynomials, and then pass it through a DAC, which is digital to analog converter. So this basically completes our overview on the fundamental topics. Now let's look at some of the advanced topics, and these are the ones which are basically used in the industry. So first one I'll talk about is the FIR filter design. So I have shown also here the methods, or some of the methods by which we design FIR filters. So FIR filters are basically used for simple filtering of the input signals to extract the band of interest from the complete spectrum which the ADC is giving you. So ADC can be operating at a high frequency, but you have only a small band of interest in that complete spectrum, and you have to select that band. So for these applications, the filtering is used, FIR or IIR both. So, and we have certain methods of FIR filter design. I have listed here. One is one of the most widespread taken up method are window-based methods. So we have different windows which we can use, like rectangle window, Hamming window, Kaiser window. What I have shown here is the window-based FIR filter design method. So ideal low-pass filter is this blue curve that I'm showing here. It has a very sharp transition at whatever cutoff frequency we want. So we want to take out only this band of spectrum, and we are not interested in the other band. But this ideal FIR filter will require a huge number of taps to be implemented, and this is generally not desirable in a practical system. You cannot be performing thousands and thousands of operations just to get the output from this filter. So what we do is we truncate the filter using some windows and still get the desired stop band attenuation of the signal. So you can see the attenuation of ideal filter is around 35 dB or 40 dB, but this is not practically implementable or realizable, as I have explained. So we take different windows around the ideal filter, and when we take the window, we have two problems. One is the pass band attenuation is not flat all through the not flat throughout the desired frequency. You can see there is a ripple here, and the transition band is not that sharp. And then the stop band attenuation has become much worse than the ideal. Ideal one is giving us 40 dB of attenuation, but the windowed ones, which are basically practically implementable, are giving us only around 15 dB of attenuation in the stop band. And then using different windows can improve the stop band attenuation further. So we can see the Hamming window, which is purple, shown in purple color, is giving us more attenuation at the higher and higher frequency, whereas the Kaiser window is not giving as much of stop band attenuation. So these kind of decisions are taken based on different constraints in our system, like how many computation can we do on the signal, or how many taps of filter. Sometimes the hardware limitation is such that we can only implement a 7 tap or 14 tap filter. So we have to live with these kind of problems. But the job of a DSP engineer would be to optimize these desired properties of the filter. And then we have least squared error method based filter design, where what we do is we take the ideal filter and then compute, and then we define a 7 tap or 10 tap filter, which is an approximation of this ideal filter, and then we calculate the squared error between the desired filter and what we are designing, and we try to minimize the error between the squared error between the desired one, the ideal one, and the practical one. So that is one way. Then we have frequency sampling method, where we start with the frequency domain. So whatever frequency domain filter we want, we take that ideal response, and then we sample it in frequency domain, and then take the inverse Fourier transform. So we go back to time domain from the frequency domain, and that becomes our filter. Then we have issues related to implementation of these filters. As I've already talked, we can implement them in hardware and software, and the issues like coefficients quantization. So in real systems, we don't have infinite precision or infinite bit width. So what happens when there is a quantization of the filter coefficient is what I have shown in this slide. So the blue curve is having filter coefficients of width 16 bits. Then red one is having 12 bits, and the yellow one is having 8 bits. So depending upon what is the capability of our system, if we are capable only to have 8 bits of filter coefficients because of memory constraints or whatever constraints that we are having, then we have to live with, you can see the pass band is having a noisy response, and the noise floor is also elevated in the stop band. So for the 12-bit or 16-bit coefficient, we can see that the stop band attenuation is going down and down, but for the 8-bit implementation, it's the noise floor is uniform at somewhere around 12 dB, minus 12 dB here. So these kind of impairments happen when we have practical limitations, and we have to optimize, as DSP engineer, we have to optimize these problems and issues. One good thing about the quantization effect is that the phase response is intact. The phase response is not becoming distorted, and this is a huge advantage, because we are designing linear filters so that each frequency component of the input signal is delayed by the same amount, And that is important because if different frequencies are delayed by different amount, then the output signal is distorted. We do not want that. We want every frequency component to be delayed by the same amount. That's called a group delay. Group delay is basically slope of this line. The slope of this line is not changing even if we are reducing the coefficients from 16 bits to 8 bits. And this is a huge advantage and property of the quantization. Then we have IIR filter design techniques. There is an important technique called zero phase filtering, which I'll be talking in the next slide. But before that, let's talk about bilinear transforms. Bilinear transform is a method where we design when we have to design in IIR filter, we design it in a continuous time system and then transform that filter from continuous time to discrete time by using this bilinear transformation. What bilinear transformation does is it maps the S domain transfer function. S domain is the continuous time system. So it maps the S domain system to Z domain, the Z transform that I've talked about. So it maps the S domain to Z domain. And this is the transformation or mapping equation that we use. But this is an approximate mapping between Z and S plane, and it's not without consequences, meaning the ideal mapping is this: Z is equal to E to the S upon Fs. But we take Taylor series approximation of this because this is not practically implementable. This will be infinite length. If we have to accurately do the transformation, it will be of infinite length. So we take the Taylor series of this expression and just take the first two terms of this Taylor series and ignore the other terms. And this is why this is an approximate mapping. And we have a relationship between the digital frequency, which I have shown as omega d, with the continuous time frequency and the sampling frequency. The sampling frequency is important, and the transformation is dependent upon the sampling frequency. If we change the sampling frequency, the mapping changes. And this is this basically warps the digital Z plane when we are mapping from S plane to Z plane, and this has we have to take care of this mapping when we are doing it. This is an important important concept to understand and use it when we are designing IIR filtering. Then we have zero phase filtering, which is a very important technique in applications where real-time constraints are not present. Like we have audio signal post-processing or a speech signal post-processing, where we have the complete signal available to us before the processing. It's not like the signal is coming in real time and then we have to process and all the parts. So we have the complete song or noisy speech signal which is there, and we have to denoise it or filter it using some for some noise cancellation or something. So we use this zero phase filtering example because if you can see, this is the original waveform which was there, and this is the noisy waveform. And if we use conventional filtering, the normal IIR filtering, the signal is the response or the signal is a little bit delayed. The noise has reduced, but there is a delay. Whereas when we are using zero phase filtering, which is this blue line, the noise has reduced plus the signal is also not delayed. So the song which is playing, it will be playing at the same time wherever you require it to play. So the sound will not be lagging behind due to this denoising operation. This is a non-causal filtering application of IIR filtering. Zero phase filtering is the non-causal procedure is cannot be done in real time, or it can only be done offline, not online. That's what I mean when I say real time. So it can only be done offline, and it needs to be how we achieve this zero delay is by designing the IIR filter by to have only real frequency response. When we have only real frequency response, then the phase will be zero. And if phase is zero, as I explained, delay, the group delay is the slope of this line. If the filter is only real valued, then the phase will be zero, or the phase will be a straight line, and the slope will be zero. If slope is zero, there is no delay. So that is why zero phase filtering is so important. Okay, so yeah, after the FIR filter design, let's go briefly over the multi-rate signal processing. I know